Morning, everyone. Today's topic is resultant of forces equilibrium of a body, and then we'll talk about rectangular components using this one, how to find the resultant forces in 2D, and then determine unknown force vectors of a particle in equilibrium. So we'll talk about the equation of equilibrium today, and then also the third one is the most important today, maybe difficult. So determine the magnitude and direction of a 3D force vector. So it's week 2, and then we'll start talking about 3D vectors. Okay. So 2D, we talked about the force. So force is a vector. It has 3 components, right? So direction, magnitude, and point of action. And then there is a method to represent this force in 2D, x and y direction, right? So we use the magnitude in x direction and y direction, and then I and j are the unit vectors in x and y direction, right? So that's what you know, right? And then if we have more than 2 forces, so maybe P and Q, so P, Q, S, so these are 3 force vectors. And then it has X and Y components respectively, right? And then we can sum X component together to find the X component of resultant, or sum of X components. And then summing Y component together to find the Y component of the resultant. So that's how we use the rectangular components, so X component and the Y component is summing those components separately together to find X and Y component of resultant. And then, so that's the rectangular coordinate method, right? So after calculating that, graphically we see this is magnitude, and then this is the direction, theta, of the resultant. Okay, and then mathematical equation to find the magnitude and direction. So magnitude, so application of Pythagorean, right, or distance formula, right? Using that one, we can find the magnitude, and the theta, the direction is using inverse tangent or other trigonometry equation to find. So using triangle, sine, cosine, tangent, and other things to find this angle. Okay, so any questions? Okay, so you watched the videos, and the free lecture quiz is great. Thank you. Okay, then moving to, it's loading. Okay. So I have first clicker quiz today here about theta, right? So first one is about the equation. Which is the correct equation to find the vertical component of the resultant force? This is the resultant force. Then what is the equation to find Fy using tangent, cosine, sine, or cosecant? Okay, during the clicker quiz, I encourage to discuss with your peers and then choose one number. Yeah. It's fine. Okay, I close after 10 seconds. Okay, great. So most of you chose C using sine, and some chose cosine. Yep. The thing is, it's correct using sine, right? Sine, and that's because theta is this angle, right? If we need to use alpha, Then to find Fy, we must use cosine alpha, right? So it depends on the angle, okay? If you chose B or D, the angle matters, and we are using the lower angle theta, okay? And then next question. So once we found the magnitude of the resultant, or F or Fx, and then Fy, then assuming we don't know theta, okay, then which one is wrong equation to find theta? What do you think? Is it inverse cosine Fx over F, so Fx over F, or inverse tangent Fx over Fy, or inverse sine Fy over F? So that means two of them are correct, and the one is not correct. Okay, I close after 10 seconds. Okay. Yeah, B is incorrect. And also D is incorrect. Okay, why B is incorrect? So I don't know. Is it? Okay. So B is incorrect. So I mark B as incorrect one. To make it correct, what should we do? Swap. Yep. So if we swap these two, that's incorrect. That's correct, right? So, and then we can use either inverse cosine or inverse sine to find theta. Okay. Great job. Okay, then now we'll talk about the equilibrium. So equilibrium is when the resultant of all forces acting on a particle is zero. That particle is in equilibrium. So resultant force is zero. That particle is not moving, right? So that is resultant equilibrium, right? So for example, if there is a particle here, A, and then 100-pound force this direction, and then the same amount of the force in the opposite direction, right? Then this particle is in equilibrium, right? So vector sum of these two forces, zero, right? How about this? We have four forces. It is tricky to say it is equilibrium or not because there are four forces. So in this case, we must use the equations. So this vector equation, so resultant vector is sum of all the forces. So vector sum of all the forces equal to zero. And in 2D, we have x and y direction, so we can use these two equations. Sum of x component of all the forces, zero. And then if sum of all the y components of the forces equal to zero, then equilibrium. Yep. So these two are called equilibrium equations. Okay? Yes?
What if only the summation of the x is equal to 0 and the y isn't? Do they have to both equal 0?
Great question. What if x component is 0, but y component is non-zero? Is it equilibrium? No. If y component is not 0, if the resultant of y component is upward, then this particle will move upward, right? So that's not equilibrium, right? So all the components must be, so resultant of all the components should be 0. So that is equilibrium. Great question, thank you. Okay, then any other question about the equilibrium? Yes?
What's the other aspect other than resultant equals 0, opposite direction equal magnitude? It's like angle of direction?
No, this contains everything. So as far as all the components of the force xy in 2D and xyz component in 3D equals to 0, then there's no force, right? No force acting on the particle. So that is equilibrium. So you don't have to consider other aspects. So this contains everything. Yep. Okay, then once we are given a problem to solve some unknown forces using equilibrium equations, the problems are typically given based on real-world situation, right? And then first thing we need to do before or in order to solve or set up equilibrium equation is plotting free body diagram. So this is kind of a problem statement. And then free body diagram is a sketch showing only the forces on the selected particle. So if we look at this problem, there is a weight here, and then two people are pulling two cables, right? And there are multiple particles to consider in this figure, right? And then which point should we use? Equilibrium equation is about 1 point, okay? Or, well, so up to far, yeah, so far it is about 1 point, yeah? And then which point should we use? A, B, C? A, right? A is good point because most likely the weight should be given and we need to find the cable tension, right? Then A is the most relevant point. If we use B or C, it's possible to set up equilibrium equation, but we cannot find anything, right? Because there's not known, right? So we'll use A and then plot the weight here and the unknown cable tensions here. And then based on this, we can set up two equilibrium equations. Sigma fx equals to 0, sigma fy equals to 0, right? So that's that. And let's try to set up equilibrium equation using this drawing. If the point A is not moving, so that means it's in equilibrium, determine the correct equilibrium equation set. So I show you these 3 sets here. And then discuss with your peers and then find out the correct equation set. So first row is fx equation. Second row is fy equation. And here, what is x component? It's cosine sine of given angle. And consider the direction too. Is this positive, x, and then this positive or this positive is y. Yeah, I close at 1 minute and 30 seconds. Okay, 1:30. Okay. There, yeah. So we have C, the most wood is the C. So let's check it together, okay? So x component of TAB, so this is TAB is this, right? And then this is TAB times cosine 50 degree, right? So TAB times cosine 50, right? And then x component of this, so it's TAC, so TAC times cosine 30, okay? It's TAB times cosine 50, okay? And then A is adding it together, but it's different direction. So if this is positive, this should be negative, right, etc., right? So this is not correct. And then what about B? Magnitude is fine, and then different signs, so this is good, okay? And then C, the same, so this is good too. And Y direction, so TAB is Y component, so this is, right, TAB times sine 50. And the TAC is y component TAC times sine 30, right? And then the same direction. So sine of these two must be the same, right? And then let's check B. And here, it's the opposite, although those two components are in the same direction, right? So this is not correct. And then this, same. And we need to check this two. And this 736 is downward, so the sign of so this number and the unknown y component should be different. So this is positive, and then this is negative, so this is correct. So that's why C is correct. Okay. Great job. Okay, then we are moving to the third objective, very important, 3D, okay? So please pay attention. So that's why I have stretch break before this, okay? Rectangular component of force in 3D. So we are adding z-axis in the force, okay? So we are using this 3D space, okay? And then the force is here, and this is origin, and then A is the target point, right? And then fx, fy, fz are x, y, z component magnitude, right? And then theta x is the angle between the force and x-axis. Theta y is force and y. Theta z is force and z direction. So we have many more components than 2D problems, right? So that's why it's easier to use vector form, this form, to express 3D vector. So 3D vector f can be expressed as fxi plus fyj and fzk, right? Using ijk, so that's unit vectors for each axis, okay? And then here, I like to connect this vector expression with the magnitude and angle. So magnitude. For 2D, we only use these two terms, but we are adding fz squared as well within the square root. Okay, so that's the magnitude. So if this is given, and then you need to find the magnitude, you are using the Pythagorean, right? Okay, very important. Magnitude here, square root of fx squared plus fy squared plus fz squared. Okay, and now I like to link this one with these three angles. Okay, so to do that, we need some intermediate procedure. So first thing, I would like to divide this right-hand side with fx, so magnitude, something like this. So I multiply the magnitude here and then divide by this one for all three. So these two should be equivalent, right? Any questions about this? So this is still intermediate procedure, okay? Then, so this vector is unit vector, right? So the magnitude of this vector must be 1, right? And then, do you remember what this is? Fx divided by the magnitude? Unit vector, so x component of the unit vector, and then that is related to directional something. Anyone who got multivariable calculus already? Or do you remember? Yes. Matrices is higher level. Matrix is linear algebra, and then it's 3D, you see. Like we can use matrix to find something, but this is called directional cosine. Did you hear about that? No? Okay. So that's the link. So this fx over the magnitude, this one, is cosine of theta x. So this angle, right? And then the y component here is cosine theta y. And then z component here is cosine theta z. Now this is the link between this vector and the angles. And then by using inverse cosine, we can find theta x, y, z, right? So that's here. By using inverse cosine of the first component is theta x, second component, theta y, third component, theta z. Okay. Do you know I upload everything to HuskyCT, right? So including slide and problem solving. Okay. Yeah. But using some notes on your own notebook is, I think, great practice too. Yeah. Okay. Then bottom line of this slide is this. So the force vector is expressed as the magnitude multiplied by this directional vector. So that is unit vector, and then a unit vector related to theta x, y, and z. Okay. So I repeat, force vector is magnitude multiplied by directional vector. So two components. Magnitude is magnitude of force, force magnitude important. And then directional vector, unit vector, it is indicating only the direction. Okay. And then we'll practice how to find the directional vector in the problem solving later too. Okay. Any questions? Okay, it's too early to have some questions. I'll show you some demonstration. So here, the force F is 20I minus 30J plus 60K pound. Okay. Then what is the magnitude? How can we find the magnitude? Using Pythagorean? Yes. Exactly. Square root of sum of each of the components. So 20 square root of 20 squared plus 30 squared plus 60 squared, right? So it's here, and then the answer is 70 pounds. Okay, so that is magnitude. And let's find the angles. So angle between the force and each axis. So that's directional cosine, using directional cosine, right? So what about theta x? Theta x is inverse cosine of, right, fx over magnitude, right? And then what's fx? 20, right? And then what is the magnitude? 70. Yeah, I heard 70. Okay, so theta x is cosine, inverse cosine 20 over 70, and then that is 73.4 degrees. Okay, let's try theta y again. So theta y is inverse cosine of which over which? Minus 30 over 70. We must use the sign as a total, okay? So if we use this one, it's greater than 90 degrees, right, of course, and then theta y is 115.4 degrees, okay? And the last one, theta z is inverse cosine 60 over 70, and then that is 31 degrees, okay? So we found the magnitude and all 3 degrees from the force to xyz axis. And if you are asked to find the vector form, then you can use this, right? So magnitude and the directional vector. Or if you are asked to find the magnitude and the angles, this is the magnitude, and then 3 angles to each axis, right? And then I'll be clear to use either method for 3D problems in the exam. Okay. Any questions? Okay. So I think this is the last page for the first part. And for 3D problem, it is very important to find correct coordinates. So what is the correct coordinate for point B? And then we'll try A as well later. So B is here, and then just note this is X, Y, Z. It's different than your math, okay? X, Y, and Z. Okay, I close after 10 seconds. Okay. Okay. Yep, we have this, right? And then let's try it together. So B is here. Oh, yeah. It's not A. Yeah, B is here. So X component of B, 0, right? And the Y component of B, it's Y component, so it's 80, right? 80, 80. So not A, not C, B or D. And then what about Z component of B? 0, because it's, yeah, here, right, it's 0. So B is correct. Great job. And then let's try A and then move on. So what about the coordinate of A? So this one, I show you the statistics. And this is the last clicker quiz. So if you didn't participate, so please use. Okay, I close in 5 seconds. Okay, good. So C or D, okay. C or D, which one is correct? So X component of A, 40, right? 40, 40, 40. Okay, and the Y component of A, 0, right? So 0, good. And then Z component of A, 30, but this is positive direction, so it must be minus 30, okay? So that's why D is correct. Okay, any questions? There was a question about axis system. So should we use this axis system if it is given in the problem? Yes, if it is given in the problem, you need to follow. Can we define our own axis system if we have freedom? Yes. Yep. So it's just axis system given in the problem, so that's why we are following. Okay. Today we have 3 problems. So first one is this. Using rectangular components, determine the x and y component which of the forces shown, and then we also find the resultant forces, these 3 forces together, right? And then the second one is pulley system, right? So that one is practice of free body diagram, how to choose interested point, and then plotting free body diagram and to find unknown forces. And then the third one is 3D problem. It's very important, so yeah. Okay, first one. Determine x and y components of each force shown. So it's kind of easy. So first one, 350 force here, right? And then what is x component? Fx is magnitude times cosine or sine, 25 degrees. Cosine, yes. Cosine 25 degrees, right? So then let's find this. So can I show you my calculator here? Right, so 317.2, right? So 317.2 Newton, right? And then you can keep going, right? So Fy is 350 Newton times sine 25 degrees, right? So 350 times sine 25. So it is 107.92, right? 147.9. So let's use first decimal place. Okay. And then, yeah, please go ahead with 800 Newton and 600 Newton, and then let's compare it together. So during the problem solving, also, I encourage you to discuss with your peers and then solve problems together, okay? And if you have a question, our TAs will walk around, so we stop them. Once you found all the components, you can go ahead to find the resultant as well. So summing all x component together, y component together. I'm starting to write down xy component here equation. And then I also share my result too. Yep, so this is what I've got, xy components of 3 forces. Anything wrong? Yes. What is wrong? Which one?
Go to the left side.
Exactly. X component of 600 Newton. It is not positive. It is negative, right? It should go. It is going left, so it should be negative, right? Anything else wrong? Okay, so it seems fine, right? So this is also good practice. So sometimes I give you some wrong answer, then you are finding my error, then it is better way to learn, actually, okay? Okay, then now resultant. What did you get? So if you calculated resultant, what's Rx? Anyone who can share? 2. Okay, 291. Okay, this is close enough. Yeah, I have 290.8 Newton. Yep, after round is so great. And then Ry, I have greater number, 1,400. 119. Sorry, 19. Okay. Anyone who got this number? Okay, good. Yep. Then it's good. So resultant can be expressed as 291I plus 1419J Newton. You can add Newton here, here, or end up this resultant force, but you need to include the units. That is good practice. Okay, and then what about the magnitude? Magnitude of the resultant using Pythagorean, right? So square root 291 square, 1419 square, right? So I have 1448.5. Okay. And then the last one, what is theta? We know magnitude, fx, and rx, and ry. So you have freedom to choose inverse cosine, inverse sine, or inverse tangent. Okay. So if we use inverse tangent, which one over which? Fx over Fy or Fy over Fx? Fy over x, right? So Fy over x. So 1419 over 291. Interestingly, that is the most common error in midterm 1. So (78.4 degrees). Okay, so this is kind of summary of 2D resultant method, the learning objective 1. Okay. Any questions? Yes. Oh. Where should I get Rx and Ry? So Rx is sum of all the x components, right? Sum of x components. So 317 plus 273, and then minus 300. Then you can find this. And then Ry, this plus, so yeah, this plus, this plus, this. It's about right, right? So, yeah. Great question. Calculator in degree mode, not radian mode. Degree mode.
Will there be like a reminder on exams?
Okay, yeah. Yeah. Yep. Do you need radians for another course? I see. Yeah. Okay. Eventually. Okay. So let's move on to the second problem then. So second problem, problem 2.67. A 600-pound crate is supported by several rope and pulley arrangements as shown. So 5 of them. Determine for each arrangement the tension in the rope. Okay, so it's here. And this crate is 600 pounds, right? And then each arrangement, there's only one cable, right? So one, and then one. So cable tension is constant, right? And then we'll assume everything is, all the cables are upright like this. So we'll ignore inclined angle. So everything is a straight y component of the forces. Okay? And then we have, although we have 5 cases, but we will solve 2 cases today, and then 3 cases in your discussion section with your TA. Okay? So let's choose which one we like to solve today. B, A, D, B and D? D, yeah, D is first one, okay. D is the first one. Okay. I don't think first come, first serve is fair, so A, okay, B, C, D, E, okay, D and E, okay. And actually, to do D and E, we need to know how to do A. So I start with A. Okay? So A, D, and E today, and then B and C in discussion section. Okay, so first question here. We have many points here. So there's a weight here, and then there's a point here, and then point here. So which one should we use for drawing free body diagram? This point or this point? Bottom one, right? Great choice, because we know the weight of crate is 600 pounds, okay? And then its weight, so always downward to center of the earth, right? Weight. And then we have upward force T here that's given in the problem. And then important thing is there is a cable tension this side as well, and magnitude must be the same, T. But what about the direction? Direction of tension in this side. Is it upward or downward? Downward. You think downward, right? So it's tension here, downward, right? But downward force is when you think about the force, internal force flow in the cable. If you think about the force effect about this point, cable tension is tension, right? There is a cable here, right? It's cable. And then this is a point, and this is cable. And then cable tension is downward. Does it make sense? It's pushing. This cable is pushing this point. Does it make sense? No. Motion is, so internal force should be downward, but when we think about in the perspective of this point, cable is always pulling, right? Like it's pulling. Oops, sorry. It's pulling. That's cable tension, right? Cable compression, not existing. Cable is always pulling the opposite side of the body. So if we are thinking about this point of action is this one, then cable tension is always outside, okay? If this is like upright, then it's upward. If it's this side and then there are all other cables, then this is this side, right? It's pulling, not pushing. So that is the most important thing about the cable tension. Cable tension is always away from the node, okay? So that's why it's important, it's upward, okay? And I know your thought process is the same direction. Internal force should be this direction, but we are thinking about this point, and cable tension is always away, okay? Okay, then we have complete free body diagram, and then there is no x component, so we can set up Fy equilibrium equations, y direction only, right? Then if we assume positive direction, either upward or downward, it's your choice, okay? Then I choose upward, okay? If upward is positive, and we have 2t upward, 600 downward, so I use minus. And then sum of all three forces equals to 0. So that's equilibrium equation. Then now, solving this equation is easy for us, right? So it's 300 pounds. Okay, and then we'll try D here. So D, we have multiple points. This point, and then maybe upward here too. Which point would you use? Bottom one, right? Good choice. Also because we have this known weight, right? So when you solve the problem, start with something you know, okay? Then if we use this point, then we have these 3 forces from one cable. So let's use OT. So magnitude is the same for all 3 sections. And then what about the direction of the cable tension? 3 cable tensions. Upward. Yeah, it's simple now, right? It's away from the object, upward. Okay. Then now, can you set up equivalent equation here? If upward is positive, we have 3 T's upward, and then 600 downward. So T should be 200, right? Yep. Yep. Okay. Yes. This one. Great question. So there is T downwards that is given in the problem. Why didn't I include this force? Yes. Similar. Can you try? Did you?
I just said it wasn't part of the free body.
Wasn't part. That's correct. It's not the part of the free body diagram. Okay. So I mentioned that we have freedom to choose any point to set up equivalent equation. We can choose this point, or this point. Okay. Then if we chose this point, then we must include this force T here. But this force is not the part of this one. This force is not acting directly on this bottom pulley, right? So that's why we don't include that one. Question?
So that means, like, if we were to look at E, we wouldn't take that small one on top of, yeah, or not that one, the one in the middle, we wouldn't take that, right?
No.
Okay. That makes sense.
Other questions? Yes.
I just wanted to make sure in the reasoning for the motion of potential, you're saying that because the internal motion, how you wrote on the arrows, is not being applicable here because it's just the tension on this one, right?
I don't think I understand your question.
So you said that the internal motion
I hear. Yep.
is like that, but it's not being used as such because it's just the tension on the point A.
Yes, you're right. Yep. Okay. Okay, good. So let's try to use E and then strengthen our understanding. So E is here, and then more complex. We have this point, and then this point, and this point, and then as she mentioned, we have choice, but we will not choose this one. We'll choose this one, and then here, this bracket is kind of rigid body, so we will consider this as entire point. And then think about the force equilibrium. Okay, and then now we have 600 pound downward. It's not inclined, it's downward. And then we have 1, 2, 3, 4 forces, although it's inclined, but we will assume it's up right here. So magnitude is the same, T, for 4 segments. And then cable tension is away from the node now. Right? And then equilibrium equation about y direction, 4T upward, 600 downward, so T should be 150. Okay, any questions? Okay, so here the lesson is if we use multiple segment and multiple cable segment, then cable tension reduces, right? So more efficient. We can use thinner cable to pull the same weight, right? Engineering point of view, right? And then another important thing is when you plot the free body diagram, we have choice to choose the best point to plot the free body diagram. If you choose wrong point, then we will not get anything. But if you choose good point, then we can solve the problem easy. So engineering is all, statics is also based on strategy, right? So, okay. Then moving on to the last one. So before the last one, let's have a quick stretch break. So stretch break. Yes. So try to make this as a habit. So when you study, right? Okay, so the third problem, problem 2.89, a rectangular plate is supported by 3 cables shown. Knowing that the tension in cable AB is here, right? That's given 408 Newton. Determine the components of the force exerted on the plate at B. Okay, we need to find the force component. Okay. So given is the magnitude of AB, so it's AB, right? And then component of the force exerted on the plate at B. So B is here, and then AB is a cable, right, supporting this plate, right? And looks like, yeah, it's following the direction of cable AB, right? And then what is the direction of cable tension exerted B? Is it upward or pushing B? Upward. Yes, upward. Yeah. Got it. Okay. And then this is vector. So let's use this cable tension as BA, starting point and end point vector. Okay, goes right? BA. So this problem is find the vector TAB components IJK, so X, Y, Z component based on the geometry. Okay, and then here finding this direction is the most important because if you switch, then that doesn't make sense, right? So once finding this one, then what should we do next to find the vector TBA? Unit vector. Find the unit vector. Yes, find the directional vector. Great. So TAB vector is the magnitude of this vector. Oh, sorry about that. I switched it. It should be BA. Oops. Starting point is B, end point is A. Yeah, please fix it. So all starting from B. Okay, and then the magnitude is given, so I'll just use it. 408 Newton and multiply by directional vector BA. Okay. And how can we find this directional vector lambda BA?
Find each of the components of the distance from B to A.
Okay, each of the component of B to A. Okay, so that is, yes, okay. So this one, correct, and then this one, this vector is a unit vector with the same direction of this force, right? So as you mentioned, finding BA vector is very, very helpful. But the magnitude of BA is not 1, right? It's something, so it is 480 millimeters, so maybe about 500, 600, 700, right, millimeters something. So it is not 1 millimeter, right? So to make this one as unit vector, we need to divide this by the magnitude of BA. Then this is unit vector, right? And then next, what should we do? We need to find the coordinate of A and B, right? So let's find it together. So A is here. So what is x component of A? This is origin A. 0. Y component? Right? 480. This is up, right? And then Z component? 0. Okay, and then what about B? B is here, right? And then X direction is here, right? So is something here? Negative 3, 20. And Y component, 0. Z component, 6. Okay, is Z here 360, right? It's positive because it's positive direction, okay? And then now BA vector is XA minus XB, right? And then YA minus YBJ, right? So this minus this, so 320I. And then this minus this, 480J. And then this minus this, so minus 360K. And then the magnitude, divide by magnitude, square root each component square. So I just use this one because negative something square, negative square is positive, right? So if your calculator, try to find the magnitude. 680. Great, thank you. So good, we found this directional vector and the magnitude is given. So we will multiply this with this. So let me write it down. So 408 times 320 over 680I plus 480 over 680J minus 360 over 680K. Okay, and then multiplying this, right? So I'll give you a couple of minutes to find x, y, z component. So I've got 192I plus 288J minus 216K. Did you get these numbers? Yeah, okay, good. So this is what the problem needs. So if it is exam, this is done. But I like to go one step forward and try to find theta x and x, y, and z. Can you do that? Yes, right? So how can we do that? We know the magnitude. Oh, no, the magnitude is not the magnitude. We know the magnitude, right? So you can write the new equation here. So this is magnitude of the force, so that matters, right? It's statics, right? Not geometry, right? So force magnitude is important. And then each component divided by the magnitude. So this is indeed what I showed you in the slide earlier, right? So magnitude times the directional vector. So when you compare this and this, it should be the same, just different numbers, but the ratio, when you calculate this one, this, it's the same, okay? And then here, this is cosine theta x, this is cosine theta y, and then this entire thing is cosine theta z, right? So let's try to find theta x, theta y, and then theta z, okay? Using inverse cosine. So this is theta x. So theta x is inverse cosine 192 over 408. Then if I use my calculator, that's 61.93, right? So similarly, you can do inverse cosine 288 over 408. You can find 4510. And then theta z, inverse cosine minus 216 over 408, then that is 121.97 degrees. Okay, did you get these numbers? Okay, good, good. So it was very quiet while solving this problem because it's new and then very difficult. So here I tried to use this 3D procedure and then calculating directional vector here. So please practice this one at home too, and also calculating theta x, y, z here. Okay. So this is all I have. Yep. Have a nice day, and I'll see you next Tuesday.